In this video, we'll talk about linear systems of differential equations and how we might think about a general solution to these systems. A lot of the terminology that's used in linear systems is the same as used in higher order equations, and it's kind of debatable which order this notation went, whether it went from the higher order equation to the systems or the other way around, but the notation is pretty much the same. So if we go from our general system, which was x prime equals vector function f of t and x, if this is linear, it means the dependence on x is linear in terms of the function f here. That means that I can actually rewrite this as x prime is some matrix function a of t multiplied by the vector x plus a vector function g of t. And it comes from the fact that, right, in this sort of system, if it's linear, then dx1 dt can't be any more complicated than some a11 of t times x1 plus an a12 of t times x2 plus an a1n of t times xn, and then plus some function g1 of t. And if I collect all of these a functions into a matrix, this big matrix a of t here, then I get the equation written in this form here. This g of t determines whether it's homogeneous or non-homogeneous. Right, if g of t is 0, then it's a homogeneous equation or a homogeneous system. And if g of t is not 0, then it's non-homogeneous, just like we'd come to expect from higher order equations as well. Now for homogeneous equations, we had the idea of a general solution, which basically meant that I had enough solutions that I could hit every initial condition that I wanted to hit for this problem. Now in this case, initial conditions look something like x at the value of t0 is some vector x1 0, x2 0, xn 0 of initial values at time t0 for this vector function. So I have n numbers there as a part of the initial condition. Now, can we have the same idea for a homogeneous system, having a general solution where we can meet every initial condition? The question then becomes, is there a way to do this? And secondly, how do we justify it? And the justification there comes down to linear algebra. So the idea is basically if I have a homogeneous system, x prime equals a of t times x, I want to write a general solution from this. So a general solution should look something like c1 times a certain solution x1 plus c2 certain solution x2 up to some ck certain solution xk of t. Now let's assume that I have an n by n system here, so A is an n by n matrix, which also means my initial condition will be of the form x at t0 is some vector with n components. How do I know if I can meet every initial condition? Well, let me plug in t0 to this general solution and see what I get. So at t0, I end up with the following. I end up with c1 times x1 at t0 plus c2 x2 at t0 and so on up to ck xk at t0. When I'm plugging in a number, all of these are just vectors. So I end up with something like c1 v1 plus c2 v2 plus ck times vk. And I want to know, can this meet every initial condition for an appropriate choice of c1, c2 up to ck? If we think back to linear algebra, this looks very familiar. This here is a span. We're looking at the span of the vectors v1, v2 to vk. If this is going to be true, what I need is that the span of all these vectors needs to be the entire vector space Rn if I want to meet every initial condition that I want. One way to do this, and the easiest way to do this, is to make sure I have a basis of Rn. And that means I need these vectors to be linearly independent, and they need to span Rn, which means I need n of them. So this k here could have been n the entire time. I want to leave it general to see what's going on. But the point is, if I want to have a general solution, I must have n, where n is the number of equations, different solutions and they must all be linearly independent. We can't have repeated solutions, like for equations where we had a double root at a value, we couldn't just use e to the 3t twice, because those wouldn't be linearly independent. That wouldn't give me the ability to meet every initial condition. So I need linearly independent solutions, as in these vectors here at the initial condition value must be linearly independent, and I must have n of them so that they can span all of the vectors that I need, so I can make sure I get the right values, can meet every initial condition. So if we have that fact, then we can justify that this expression here is a general solution to this homogeneous system here, because I have enough things I can meet every initial condition, and I can do whatever I want, and they all solve the problem. That's the idea of a general solution for these things. They look very similar to what we had for equations in the past, but we need to make sure that, again, these vectors here are linearly independent. Like, we had to make sure that our solutions before were linearly independent to make sure we could write our general solution. The same is true here. And now that we have the knowledge of linear algebra and the language of linear algebra to talk about this, we can discuss these vectors being linearly independent. And you can see how you figure this out, right? If you stack these in a matrix, you can use row reduction to figure it out. All these would be ways you could figure out if these are linearly independent to let you know if this is a good enough general solution to solve this problem. And in this case, you can again solve system equations to solve for the C1 and C2 to make this work, just like we did before. And that will allow us to justify this as a general solution to this problem. So that's the idea of what this looks like, what a linear system does and how it behaves, as well as what a general solution might look like to this kind of problem. And we'll see many examples once we start trying to actually solve these equations and solve these systems. We'll see equations popping out in this form and understand this is where it's coming from. It's coming from the structure like this that gives us a general solution as a linear combination of some basis solutions for this problem.